So today we'll learn about linear regression and a lot about it. In fact, not just about like the ordinary least square regressor, but we'll also learn about regularizations. And I think I've discussed about regularization with you before. The regularization is adding some slack terms to the loss function so that you can develop or sort of modify the loss function in certain ways, and those modifications have certain ways of changing the way the optimization process behaves, and we'll be studying them in like very great detail today. So these are sort of the notes which I've prepared, and I've already made available to you. And these notes have most of what I have. I have taken the help of ChatGPT while trying to make these notes, and have been really useful to me. So first we'll try to see what linear regression is. I think I have already taught a little bit about it before, but we'll just go on a very quick sprint over the very fundamentals of linear regression, and what exactly are we trying to do, what exactly are we trying to solve, and then we'll go back like directly head on into the regularization part. So for the contents, we'll be checking the problem setup and the goal of linear regression, obviously. Then we'll be checking empirical risk, generalization risk, and the loss functions. Then we'll know about ordinary risk squares, so that's something that we have already sort of known about, gradients and batch gradient descent. And then what are we exactly optimizing and why are we optimizing that? Then we'll go to what coordinate descent is, what gradient descent and coordinate descent differ, like in what kind of situations you can do gradient descent and what kind of situations you cannot do gradient descent, and for those situations we get to know more about coordinate descent. And then we'll go about differential convex functions, then how to create residuals, the entire concept of residuals which will use for coordinate descents for OLS, that is ordinary least squares. And then we'll learn about subgradient optimality and for convex but non-differentiable objectives. Then we'll learn about subgradients, subdifferentials, and then we'll learn about the condition of subgradient of optimality. And then we'll learn about how to apply subgradient optimality to the Lasso coordinate problem. And then we'll try to solve for the Lasso optimum. And then we'll combine all the cases and we'll create something called the soft threshold solution. And we'll try to interpret the soft threshold solution of Lasso. And then we'll also discuss about how you can use certain changes in your gradient descent technique to accommodate for soft threshold solution, or you can also say shrinkage thresholding solution. And that gives rise to proximal gradient methods. And from there we'll try to decompose the problem, and then we'll introduce a proximal operator, and then again we'll learn about proximal gradient update rule. We also call it iterative shrinkage thresholding algorithm. Iterative shrinkage thresholding algorithm, that is what proximal gradient update rule is. We'll try to learn about the convergence of ISTA, and then there is this fast iterative shrinkage thresholding algorithm, which is the accelerated version. We'll just sort of have a little bit of touch on that. We'll try to interpret, and then we'll try to learn about bias variance trade-off, which is quite important because at the end of the day, the entire motivation of using regularizations in linear regression sort of at the end of the day, you'll realize why this is important, and that will be evident in the bias variance trade-off part. So, so first we'll try to set up the problem, right? So we have observed n examples with, there are total p features. So there are, xi is basically rp, which basically means that there are p real numbers, and when we get yi, which is a real number in response. So this is obviously a regressor problem. When you realize, so how do you differentiate between a classifier and a regressor? You just check the yi, right, where every input has a particular output, and if the output belongs to classes, then we call it classifier. Otherwise, if it belongs to a continuous range, for example, here real number is continuous. So it could be like anything, and it doesn't really belong to a class. But we can obviously always convert regressors to classifiers by making buckets. So as real number is a continuous set, then we can bucket, for example, like if my number falls between 0 to 1, then we'll be putting it into one particular class. If the number falls between 1 to 2, then we'll be putting it in a different class, and that's how we can make a regressor a classifier. And we'll be learning more about it in logistic regression and neural networks. Like the entire point is how they convert regressors into classifiers using this bucketing method, right? So for now, we'll be stacking features. That is the design matrix, whose basically ith row is xi and the responses are y. So then what our affine linear regression model, affine is basically a polynomial function on x, and then you find that the yi hat, which basically is the the generated yi, is basically what the output is out of your weight vectors. So here, for instance, beta naught is a bias, and beta j is the weights for a particular parameter, and then we are summing it up over all the so we are summing it up over the entire feature space, and then we are getting something like xi transpose beta plus beta naught. So that is very simple. That is just this equation of a hyperplane, and we are trying to fit a hyperplane over a set of points, which the points which belong to there could be multiple parameters which are which could represent those points, and what we are trying to do is we are trying to create a hyperplane which does justification to all of these parameters. So I think these things were pretty clear, so I won't really go into much depth of it for now. By that I basically mean that when you did linear regression for a 2D, where basically that was like 1D parameter and the other, the y was just the label, in that case you can, it is very obvious how to do the linear regression, but here in multivariate cases it's just useful, like linear algebra is extremely useful because you are working with like higher dimensions. So we are going to use a lot of linear algebra terms throughout, and if you have any doubts you can just and of course, okay, I just prepared the notes like very fast, so there could be like certain errors so there could be not just errors in the nodes, but there could be errors in representations of the equations, and those things will also be corrected once we sort of go through. So yeah, so for now we'll be taking a look into what loss functions are and what empirical risk is. Empirical risk is very simple. So where the empirical risk is the average loss over the data. So for example, you have a particular training data, so you just define empirical risk as the loss over just the training data. So you have a particular set of data received from a distribution. So you just define the empirical risk as for all the points. For example, you are trying to develop a loss function called like mean square error loss. For instance, here MSE is being used, which basically means that we are going to take the difference between the labels and we are going to square over it. Okay, so that is the reason why we are doing mean squared over here, because taking squared is one of the ways to get rid of the cancellation effect of positive and negatives, and I think those things are very obvious. We are just going to like sort of skim through them. So the empirical risk is the average loss over data. What generalization risk is? So generalization risk is more important. Okay, so that basically is when you make a model, what is the expected risk over all possible data points. Now the fact is that you do not know what data points are there with you. You only know the training data. But what we are assuming right now is that all these data points are being sampled from one distribution. So there is one particular distribution somewhere. It could be a normal, it could be some multivariate distribution up there. And what we are trying to do is we are trying to sample data points out of the distribution. And we are fixating the distribution for now. We are saying that, let's say that there exists a distribution from where the initial points were sampled. And we are finding the empirical risk only on those points. The generalization risk could be when I know the loss over the entire data set. Why is that important? Because it could be sometimes that the empirical risk is low, but the generalization risk could be still high, which basically means that we could not learn the model over the entire possible data set. We could learn the model over the training data set, but we could not learn the model over the entire distribution. Which could mean two things, which could mean that our model has certain issues in it, in the complexity of the model, or we could not understand the data distribution properly, right? So there are two things. So again, these are ways you can represent risk, that is empirical and generalization. So as of now, we are just trying to find the empirical risk. Obviously, like generalization risk is not something that you can find out of data. You'll have to take an expectation over empirical risk over the entire data points sampled from a distribution to get the generalization risk. So these are like very basic concepts of machine learning. It's probably that's something you guys should know. So I just pointed that out. Uh, right. So basically the MAC loss function is just yi minus beta naught plus xi transpose beta whole squared. So I'm just going to skim through them. Do you have any doubts here? Which is basically the L2 norm of beta naught and 1 plus x beta, because 1 is basically the bias term which you just took inside the beta, so that is how it sort of looks like for now. Uh, any doubts or something like that? Anything to comment? So I'm waiting for your comment, then I will go forward with it.
No, it's alright.
Okay. So we realized what empirical risk is, and basically this is ordinary least square. So what you just saw here is basically ordinary least square. We just call it ordinary least square, and what we are trying to do is we are trying to optimize on that. So the entire point in machine learning is optimizing over the weights, because at the end of the day you need some weights which represents the data well, and that is how do you do that? You define a loss function and you try to minimize the loss function. What you mean by that is basically you try to define something saying that, like if this parameter is high, that means our model has not trained on the data points. So what we try to do is we try to minimize some parameters. So for example, here we are trying to minimize the mean squared error, which basically is the distances between the hyperplane and the points, and then we are trying to like minimize over the sum of basically the average of them. So that is something that we are trying to do over here, the mean squared error. So by that we are trying to get a hyperplane from where we can basically state that at least for our entire training data set, this entire this mean squared error for all the data points would be minimized, which basically means that we have we have gotten to an optimum. We cannot get better for this particular loss function than this. Yeah, obviously there are other ways to define your loss function, but when you define a particular loss function, you try to minimize on that, right? So these are simple things. Batch gradient descent is just something that updates all the coordinates simultaneously, and gradient descent is where you do like for one particular coordinate, you do like you find the gradient of that coordinate, and then you do a descent on that coordinate based on the like obviously you do something called a stochastic gradient descent, which basically means that you pick a data point at random and then you try to train the weights using gradient descent. So that is something that you do. Batch is where you take multiple points at the same time and then you try to get the coordinates simultaneously. So these are not like very important. I mean, these are important, but you can just take a look at this, like sort of skim through the equations. You just need to make sure that you understand all of them, and that's pretty much it. It's not very difficult, right? At the end of the day, the motivation sort of remains the same, right? So yeah, what exactly are you optimizing? We are minimizing the empirical risk, and so this is also important, and we will be taking a look about this later. So what I basically mean by if there is a a random Gaussian noise, then what we try to do at the end is we try to make the model unbiased, and we'll be taking a look into what I mean by that later. Yeah, so coefficient level interpretation under standard assumption, and for pure prediction we prioritize generalization error, cross validation, and regularization. So that is for pure prediction, and I just explained what generalization error is. At the end of the day, you would want your model to work on test data. You like just by making your model work on training data, you have just done half the job. You need to make sure that your model works well on the test data, and that is where generalization risk comes into play, right? So now we'll be taking a look into like different methods in which we can make the linear regression better. And what do I mean by better? So there are certain issues with linear regression, right? One of the bigger issues is that uh, the OLS, the method that we have discussed until now, the ordinary least squares method, this method is very prone to overfitting, right? What exactly is overfitting? Well, overfitting is where your model works really well on the training data, but it fails on the test data. That means your empirical risk is very small, but your generalization risk stays very high, which basically means is the mathematical depiction of overfitting. And that happens, and we'll learn why that happens while we are trying to mitigate that problem, right? Okay, now I'll be teaching you some mathematical constructs, right? How do we do certain things mathematically, and then we'll be using them while we learn regression techniques, right? So one of those first mathematical constructs is called coordinate descent, right? So uh, coordinate descent and gradient descent are two fundamental iterative optimization methods used in convex and non-convex problems. Both aim to minimize the cost function, but they update parameters in fundamentally different ways, right? So what is the goal? Well, the goal is to minimize the loss over all the parameters. So what you do in gradient descent is you do a gradient step over all the parameters at the same time. So what you do in gradient descent is gradient descent moves along the negative gradient of f using a small step size. We call that a learning rate. And what we basically do is this is the next iteration of our parameters. This is the previous iteration of our parameters. And we get the next iteration of our parameters as the previous iteration minus learning rate times the grad of the loss function. Right? Right? That's clear. At the end of the day, what happens is our loss function gets minimized because we are moving our gradients we are moving our weights in such a way that we are trying to move towards the gradient of the loss function. That basically means that we are trying to move towards the global minima of our convex function, right? Right? So that is what gradient descent is. But what coordinate descent is, coordinate descent is it optimizes one coordinate at a time while keeping the others fixed. What it basically does is it keeps all the parameters fixed. So let's say like here, for instance, like you have like bunch of parameters, right? Like you have like n parameters. Like your weight matrix is basically your weight vector has like n of them, like w1, w2 up to wn, right? So here, for instance, like you have up to p, right? Like there are p of those parameters. So what you try to do is you fix all the other parameters and you do update on only one of those parameters. And then you fix that parameter, you do update on the second parameter, right? So, okay, something sort of clicks from this idea, the coordinate descent idea. To me, what immediately clicks is like if all these parameters are independent of each other, then gradient descent and coordinate descent are supposed to give you the same result. Does that make sense? Does that make sense?
No, can you say me
Wait,
the
Right, right. So,
wait.
no. So
Um,
basically, when you are trying to do gradient, when you are trying to find gradient, what do you do? What do? You do del f by del bi, right? You try to make a matrix of like what do you call it? Like dou f by dou bi. Essentially, that basically means that you are taking the partial derivative of f with respect to bi, like beta I, beta like beta 1, beta 2, beta 3, and then you are trying to make that entire matrix, right? So that is basically, so while doing a gradient step, you are anyways not taking the influence of other parameters because you are doing partial differentiation, right?
अच्छा
So there, when we are updating one parameter, it is independent of the other parameters. And that is what is happening here as well in coordinate descent because we are updating only one parameter, keeping the others constant. And we already know that this parameter doesn't depend on the other parameters. So we can update this parameter to its minima and then go to the next parameter to update it to its minima.
Acha, acha.
So they, like, intuitively, also you'll see mathematically why they actually give you the same result for situations where you can do both gradient descent and coordinate descent. Okay. So here it is written as well, the mathematical relationship of differentiable coordinate convex functions. So the gradient descent for the coordinate case is equal to give you this.
আচ্ছা ইটারেশনে যেটা বলছিস, so every coordinate descent, so every time I call I minimize it,
Yeah.
So it will be considered as one iteration, and then I move on to the next iteration.
Yeah, so basically what we are trying to do is we are trying to get a closed form solution for one particular parameter. So we are not doing any descent. Okay, we are trying to find a closed form solution. Understand what closed form solution means?
No.
So closed form solution is like where you just like do a derivative. You just do the derivative over one parameter and you set it to 0, and then you automatically find the optimal parameter value. So you do not have to do a descent to find the optimum because you have a closed form solution in the first place. Right? Like there are, so you can literally just set it to 0 and you can find the minima. Like what do you do while trying to find the minima of a function? You differentiate it and you set it to 0. Right? And then you and then you find the x at which the gradient is 0. Then you immediately find a closed form solution. But that is not possible for all kinds of functions, and that is the reason why we do gradient descent. Like when we do not even know if our function has a convex, like has a minima or not, then those things become more obvious. Like when our optimizer in itself is so complicated that differentiating it and setting to 0 is just not possible for us. In those cases, we try to find gradients and we do try to do gradient descent, right?
Acha. Okay.
So in coordinate descent, because you are converting the problem to a single variable problem, you can always find a closed form solution. And we'll see how to do that. Right? We'll see how we actually find the closed form solution for in case of coordinate descent. Right. So these things are okay. Now the thing is, how do we do coordinate descent? And for that we need to know an important concept called residuals, right? So what exactly are residuals in linear regression, right? So let's say that r is equal to y minus y hat, right? So which is basically the like y is the true prediction and y hat is the predicted responses. So yeah, so it is something like y minus beta x, right? X beta, whatever, beta transpose x, whatever you write it that way. So what you try to do is you try to quantify the model's prediction error at each observation, right? So you try to get something like Ri is equal to yi minus xi transpose beta. So that is the prediction error only for that particular observation. So only for xi, what yi you are getting, so that is that signifies Ri, right? So you can actually so the minimizing the residual sum of errors equivalent to the minimizing the mean squared error, right? So you can just minimize over the sum of errors Ri because they are all independent to each other. It is equivalent to minimizing the mean squared error. So what we basically do is we try to define something called the partial residual, right? So like let's say that xj denotes the jth column of x, and we'll define the partial residual that excludes the contribution of coordinate j, right? So here you see, here it is very important. So r minus j, which basically means that we have thrown away the contribution of j in our residual. What that brings is y minus summation of all k that is not j. That means I have removed j and I am taking a summation over all the parameters xk beta k, right? which basically is y minus x beta plus xj beta j, which is r plus xj beta j, right? So this is just simple math. So what do you do, like when you try to optimize along one particular coordinate, then you can write it in this form. Like you, let's say like this is the entire loss function. You can write it in this form, right? 1 by 2n r minus j minus xj beta j. So this is what we gotten from here. So r is essentially r minus j minus xj beta j. So we are just keeping r, instead of r we are keeping r minus j minus xj beta j. Okay, so this is the loss when you are like when you keep one, like all other parameters constant, that means r of minus j will become a constant, right? So you do not really have to worry a lot about r minus j, and that is the reason why we use this formulation of residual. So we are doing coordinate gradient descent, which basically means that we are doing gradient descent over all coordinates separately. That means we are fixing all the other coordinates and we are doing gradient descent over the first coordinate. Then we are fixing the first coordinate and from the third to all coordinates, and we are changing the second coordinate. Then we are fixing first and second coordinate, and from fourth to all other coordinates, and then we are changing the third coordinate. So that is what we are trying to do here. So what we are doing here is essentially we are trying to minimize the loss of that particular coordinate, and then for that what you see is the r minus j minus xj beta j. So here you see that beta j is there in our loss, right? So beta j is there in our loss, and this entire loss is it represents the loss of the entire problem, because obviously, right, r like r is equal to r minus j minus xj beta j. So we are just keeping r minus j minus xj beta j, which is basically r. So what you are trying to say is we are trying to minimize the loss over all beta, right? So this is what you are trying to do. So first let's expand on it, just taking square. So what you find here is like r minus j transpose r minus j minus 2 beta j xj transpose r minus j plus beta j square xj transpose xj, which is again the loss. You try to differentiate the loss or just beta j. Now you know that this is the loss, and you are trying to optimize the loss only with beta j, only over one parameter. So we take the loss over only one parameter. We do not take the loss over the entire parameter set. And once we do that, because this entire thing is just dependent on beta j, and r minus j is a constant, so the r minus j comes out, and this once we do the differentiation, it comes out as minus 1 by n xj transpose r minus j minus xj beta j, and from here you get beta j as xj transpose r minus j by xj transpose xj. So this is a closed form solution for OLS, ordinary least squares. So this is a closed form solution for one particular parameter. Is that clear? So here what I meant by closed form solution is, here you are not doing any gradient step. Here you do not see any steps, like you do not see any learning rate. What you see is the parameter. So this also constitutes all the parameters. So here you see only parameters. So with the help of only parameters, my inputs, x are inputs and not parameters, I'm sorry. So with the help of just inputs, r minus j also contains just inputs and the current set of parameters, right? So this is with the help of only the inputs, we are trying to find beta j, right? Okay, wait, might be a little incorrect here. This is the sorry. This is the coordinate descent update. This is not the least square. So I was actually a little confused because this contains beta k in it. So this contains a set of parameters in it, or no? Okay. Yeah. Right. No, this is indeed the closed form solution. I was not incorrect. R minus j is not dependent on beta j. R minus j is dependent on all other beta which is not j. So those are constants. So at the end of the day, you are just getting beta j from a bunch of constants and the input at j, at the jth element. So that is xj transpose. So again, like all of these are like, you do it mathematically and you find like a way to represent beta j. So this is how you can represent beta j. So what we can get from here is uh, so right. So what we can get from here is that from the on the ordinary least squares, this is very simple to do, right? Why is it simple to do? Because you can write something like this. That is del L by del beta j is equal to minus 1 by n x j transpose r minus j, which basically is the when you differentiate the loss function, then you get this, right? But what happens if the loss function is not differentiable? And that is where the real fun begins, and we'll be learning about it, right? So now we go to something called this subgradient optimality, right? This is for functions that are convex but not differentiable, right? So for example, when you define a regression like the Lasso regression, L1 regularization, which basically means that you are adding with some lambda, which is a hyperparameter, you are adding the mod or the absolute value of beta j to the problem. Clear? So this is, for example, like Lasso regression over one parameter, because you are adding an absolute value of the weight uh, to the loss function, which basically means that you are trying to now optimize this loss function, which is not differentiable at 0. So what we try to do is we try to define something like something called a subgradient. Now here there are a lot of mathematics going on over here, but I'll tell you what exactly subgradient is. Right? So I'll just tell you on a like very like sort of graphical way. So first is we try to get right. So this is the graph of y equal to mod x, with y equal to absolute value of x, and we can see that it is not differentiable at 0, right? So this function is not differentiable at 0. But what you can try to do is you can try to define a function. You can try to define a function which is indeed differentiable at 0. Okay, which is indeed differentiable at 0, but with a like small epsilon gap, it converges to y equal to mod x. So I'll give you an example of such a function. Moment, I try to give you an example of a function like that. So something like like n equal to, let's say, 10, and I try to define like uh, you know, like x, so y equal to x to the power uh, 2n, like plus 1, and you take a power of this 1 by n. So, yeah, 2n plus point 0, 0, 0, 0, 0, 1, or you can basically make this like as close as possible. So this is what I try to mean. So now you can, like, so n can be an arbitrarily large number. So n can be, for example, something like, let's say, like n is here. So n can be something like 100, for instance. It's 100 is not. So you can try with like 19 or something. Anyway, the point is like you can like add like zeros to it, and then you can see that this function is differentiable entirely, right? But what we are trying to like at the end of the day get is something that approximates to y equal to mod of x. We are trying to approximate a differentiable function to y equal to mod of x, right? By that I basically mean that uh, so by that I basically mean that whenever you are trying to define something called a subgradient on a point which the function is not differentiable at, then you try to take the derivative of the function which is approximate to the initial function. So we just saw one function like that. and you try to like assign those values of derivative. Now the thing is, I'll tell you. So here, for instance, the derivative of this function, so like, so as you see, like on this region, so where you just track my cursor, on this region the derivative is -1, on this region the derivative is 1, but in this region the derivative is 0. So what happens is, we, like, our derivative decreases from 1 to 0 and then goes to -1. That is what would happen for a convex function which is continuously differentiable. The derivative, when you go from the positive to the negative side, the derivative will slightly, it will gradually decrease from 1 all the way up to 0, and then it will go back to -1. It is a gradual process, right? So there will be a point where the derivative is indeed 0, right? But in case of mod of x, right, that does not happen, right? So it is like at one point, suddenly the function, like there is no derivative at the point, so it's not differentiable at 0. We call that is the entire problem that we are facing. So what we try to do is, we try to say that the derivative of mod x is, so this is the sub differential, we call it sub derivative, it's just a name. So the derivative, which is redefined derivative, saying that it is +1 for x greater than 0, well and good, we know that it is differentiable. -1 for x less than 0, again well and good. And for x equal to 0, it is between -1 to +1. So as we do not know the exact derivative, we give it a range, saying that, let's say that the derivative is -1 to +1. We can definitely approximate another function to mod x, and that function will have derivative of -1 to +1, not exactly at 0, but from 0 minus epsilon to 0 plus epsilon. That is how the function is supposed to behave, right? So we are just trying to approximate mod x into a continuously differentiable function, and this is an extremely important concept, because this is exactly what you do when you find a non-differentiable function and you try to do gradient descent. You try to do something that requires gradient to be defined at all points. So you just define the gradient at all points. You just hand define the gradients by some sort of an approximation, and that is exactly what we are trying to do over here. Okay. So now we try to apply the subgradient optimality to the Lasso coordinate problem, right? So again, so this is our Lasso problem, and we try to like get the derivative. So now we can define the derivative of, like, so lambda times derivative of beta j. Now that is something that we define, right? That is something that we just define, so we can write it. Like God has given us the rights to write it right now, just because of the fact that we just defined this term. Otherwise, if this was not defined, then we couldn't have written it. So now, how to interpret this, right? So to interpret this, there are three cases. That is, when beta is greater than 0, then beta j is going to be z minus lambda by a. So z is basically just this z, right? Okay, so when beta j is less than 0, so in that case beta j is z plus lambda by a, because again, like, you are just setting the derivatives to be 0. Like, this is exactly what you're trying to do. Like, this derivative, this is what you're trying to set at 0. You're trying to find a closed form solution to the Lasso regression problem, right? So you find beta j for when beta j is less than 0, and you also find beta j for when beta j is greater than 0, which basically means that you're trying to find optimals for all possible values of beta j. And then when beta j is equal to 0, then you know that the delta is -1 to +1, and as per this condition implies that the mod of delta has to be less than equal to lambda, right? So whenever this z lies within this minus lambda to plus lambda, then beta j is being set to 0. This is a very, very important result. This is a very, very important result, and we'll be learning why. So again, the piecewise solution. We'll look at the piecewise solution. We are trying to find an optimal beta j. That is the coordinate descent. We are trying to find a coordinate descent of one particular parameter, that is beta j, on the Lasso regression problem, which has L1 term, so that is not differentiable. So we just defined the derivative for that, and according to that, we found out that for z greater than lambda, we have z minus lambda by a. For z less than minus lambda, we have z plus lambda by a, and for z between minus lambda to lambda, we have beta j is basically set to 0, right? 0. Sorry, the notations are not written properly. So it is 0 for mod of z less than equal to lambda. It is z minus lambda by a for z greater than lambda, and it is z plus lambda by a when z is less than minus lambda, right? And we can actually compactly write it using this soft thresholding operator. We call this s of z comma lambda a soft thresholding operator. S of z comma lambda is basically sine of z maximum of mod of z minus lambda comma 0, which is basically this. You can verify. We are just writing it as a single line, and then we can write beta j star in a closed form way, that is 1 by a s of z comma lambda. So we defined a few things here. It might get a little overwhelming, but at the end of the day, we are getting a closed form solution of the optimum value of beta j, and that is beta j star, and that is 1 by a s of z comma lambda. Right. And then there are methods like proximal gradient methods, where again you do something that we did right now, right? We try to define gradient descent for something that doesn't have gradient. So here, for instance, we do not have gradient, so we try to define gradient first, and then we try to like decompose AF as G beta, where G beta is convex and differentiable with a Lipschitz gradient, and H of beta is convex but is possibly not differentiable. So which basically means that we are dividing this function into two parts, and we are going to work with gradients in two separate sections, and we call it the proximal operator, where we have a loss function. One is a minimizer over gx, and the other is a minimizer over hx. And how do you use the minimizer over hx? You just use the soft thresholding operator. You can take a look into all of this. This is just very simple things at the end of the day. And these are the update rules. You can define update rules based on our newly defined soft thresholding operator. So all of these update rules are going to have s in it, which basically is the soft thresholding operator. Convergence, again, not very important. I mean, it is important, but again, like at the end of the day, it depends on whether your G is a Lipschitz continuous gradient or not, and that is something that you're supposed to know. I mean, it's a convex optimization, right? So that is, yeah. So what did we get from here? Yeah, that is very important. What we exactly got from here is an solution of our Lasso regression problem, right? So what exactly is the solution of the solution? Let's try to get into it, right? Yeah. So this is what it essentially is, right? So uh, first we fix all coordinates except beta j, and we try to minimize this 1D subproblem, which is just for beta j, right? That is r minus j minus xi beta j squared plus lambda beta j, and where r minus j is y minus the summation over xk beta k, where k is not equal to j, and then we expand the quadratic term, and from here we get a is 1 by n xj, the like xj squared, right? And we also get z is equal to 1 by n xj transpose r minus j. So this is what z is. Okay, we'll try to refer to it. So whenever I'll try to explain to you something using z, so we'll try to refer to it. So we got the values of beta j star, right? So which basically means that we got the values of the optimal values of a particular parameter. Now these parameters, so here for instance, it is dependent on lambda. Obviously lambda is our hyperparameter, and that is something that we set ourselves. It's completely on us, right? So this turns out to be z minus lambda by a when z is greater than lambda, right? So what exactly is z again? So it is 1 by n xj transpose r minus j, right? So which basically means that this contains the information about the correlation between xj and r minus j, right? And r minus j is basically y minus summation of k not equal to j xk beta k. So it basically means that the r minus j encapsulates the information about all the other set of parameters, and xj gives you information about this particular input. So that is the jth input, and r minus j gives you information about the parameters which are not related to j at all, right? So this term is essentially the correlation between the jth input and all the other parameters, right? So what that gives us is when the correlation between the parameters, let's say like when I chose like the parameter j, when I'm studying parameter j, if my correlation of this parameter with the other parameters is very high, right? If my correlation between this parameter and the other parameters is very high, that means at that point what happens is my z becomes high, right? So we shrink z by lambda, but we do not set it to 0 because z is not less than equal to lambda, right? So we do not set our beta to be equal to 0. However, when we go to the next iteration, so let's say when we are going to the like when when I'm trying to optimize for x1, so x1 is done. Let's say now I
Some
go.
other different.
Are you back? Yeah. Are you back? Samita, yeah, fine, right? I hope things are fine. I'm audible and stuff. So yeah, right. So now what happens is when you set xj to x2, now that you have already optimized for x1. So let's say x1 and x2, they have very high. So basically, beta 1 and beta 2, they are supposed to have very high correlation. So uh, I mean, you obviously do not know anything about beta, but you know about x. But so basically, you know that like there are a bunch of parameters, and in one of those axes, uh, like let's say like two of those axes are very highly correlated, right? So like x1 and x2, as in the input space for like the first coordinate and the input space for the second coordinate are very highly correlated. What happens in that case is, so your r minus j, when you take like when you throw the uh, like your particular so let's say like you are sitting on x2 right now, so when you throw x2 away, right, so you are trying to check whether the variance of the loss still exists for x2. So you are trying to check like when you do not consider x2, then are the other parameters contributing towards the loss or not. And then you have already optimized x1. In that case what happens is your r minus j and xj transpose, they become perpendicular to each other, right? So again, this might be a little confusing. So what happens here is exactly, so for one x, so for x1 you have already optimized the set, you have already optimized x1, uh, basically you have already optimized beta 1, and now you went up to beta 2, you are trying to optimize for beta 2, and you have x2 transpose r minus 2. So let's say like you only have two parameters. So r minus 2 is basically when when k is not equal to 2, so that basically means y minus x1 beta 1, right? So you know that y is already influenced by beta 1 a lot. That means that when I like subtract x1 beta 1 from y, if x1 beta 1 already represents the variations in y, then y minus x1 beta 1 is not going to leave anything for beta 2. In that case, x2 transpose r minus 2 is going to be almost 0. That means in such situations, z becomes almost 0. Like z becomes very small. And why did I tell you this? Is because when z is small, like when the value of z is small enough, then what we are trying to do is we are trying to set the weight for that parameter to 0. We take that and we make it 0. We make it straight up 0. which basically means that when you do lasso regression, when you do L1 degradation, then if two parameters are severely correlated in your input space, if you chose arbitrarily a bunch of parameters and if two parameters are severely correlated, what lasso regression tries to do is it tries to keep only one parameter and it tries to set the rest of the parameters weight to be 0. Okay, so this is a method of dimensionality reduction. Lasso is a method of dimensionality reduction where, let's say, you have this very classic example of where you are trying to try to predict the price of a house. Let's say you are trying to predict the price of a house, and the set of parameters you defined for that is like the size of the floor, the size of the land, and the altitude. Okay, like wherever like it is present in the mountain or it is present in the plain. So it is very clear, right, that size of the floor and the land will be very strongly correlated. If the land is more, then the house size will also be more. People will try to use most of the land, right? But it is independent of altitude. Like if altitude is a completely different parameter. What happens here is when you use lasso regression and you try to estimate over the house price using these three parameters, your lasso regressor will set one of those weights of those very strongly correlated parameters to 0. So your lasso regressor will say ki bhai, I can already understand that like the size of the land is something that also represents the size of the house, so you do not need any weight for the size of the house. Let that weight be 0. Let the weight of size of the land be some positive number, and the size of the and the altitude be some positive number, and we will try to make a function which only takes these two parameters and gives me the final output. So here you are not losing anything because you already knew that two of these parameters are so highly correlated. One of those parameters are unnecessary. You don't even need that parameter, and lasso regressor actually finds that out for you, right? So this is one of the biggest powers sort of lasso regression, where if there are very strongly correlated parameters, then it just sets one of those parameters to 0. Lasso has the power to set things to 0 because you saw, right, like it literally sets things to 0 when z is less than equal to lambda. So once you have optimized one parameter, you go to the next parameter and you find that r minus 1 becomes 0 for that particular parameter because one of the parameters is already optimized, and immediately then z becomes very small, and then beta j star is set to 0. So that means your weight for that particular parameter is set to 0, and that is what lasso regressor essentially does. And then we'll look into different ways in which this can essentially help you. But the main motivation of lasso regression is to remove correlated parameters. That is the main motivation of lasso regression, right? You use lasso regression to make sure that your correlated parameters are not all taken into account. And I think this is something that was present in your notes as well. So that was obviously not derived, and we just derived it for you. In Samaita's notes, we have this information. So we have this information. Yeah, see, so this information, it says that some coefficients become exactly 0. It adds L1 penalty, and it also gives you this thing, which says that, yeah, when features are highly correlated, coefficients in linear regression becomes unstable. The model struggles to decide which variable is more important. Small changes in data makes big changes in coefficients. Coefficients may become very large, which might cause overfitting again. So this is entirely what is happening. So what we try to do is we try to shrink the coefficients. As you saw that there is this thing called z minus lambda. So like jodi amar coefficients, like my point is like even if my coefficients are high if even if there is no there is no such big issue of correlation, and even if the z is high, we still decrease it by lambda, we still get something like z minus lambda by a, so we still get a shrinkage, right? So that gets up, the problem of overfitting is gone. So here you see shrinks correlated feature coefficients towards each other to stabilize them. This is what ridge regression does. They have the same purpose. And lasso regression selects one feature and reduces other features to zero. So it basically does feature selection. It's very clear what is being done, right? So it selects one feature, and when you go to the next feature, then this z becomes so small that we set it to zero using suboptimality of the basically the proximal gradient, right? So this is exactly what lasso regression is, right? And ridge regression is not very difficult to study. You know all the concepts, so it's just about in ridge regression you don't even have to do that. It is like way easier to analyze ridge regression because you don't have to do this coordinate descent or anything, because that is a completely differentiable function. So you can just do gradient descent, right? So instead of taking the L1 norm, it takes the L2 norm, right? So that is how things are. Right. So we'll directly go to bias variance trade-off for now. Here, just there are in Lasso the proximality corresponding to soft thresholding, enforcing sparsity at each iteration. Sparsity basically means that there are some weights which are set to exact zero. So that basically means sparsity. ISTA alternates between gradient descent and the MC term, and shrinkage via the L1 penalty. So this is what ISTA does, and you can check the ISTA update rule over here. It is present here. So now we go to bias variance trade-off, and it's very important. So how do you find the bias and how do you find the variance of a particular data set? So we'll be trying to look into like very some intuitive ways to understand what bias is and what variance is. So let's say like you have a design model. So you have a beta star, which basically means that your parameters have been optimized, right? So your parameters are optimized, and you are getting y is equal to x beta star plus epsilon. And your entire point is that our expectation of epsilon over multiple choices of x over our entire distribution should be 0, right? Which basically means that our model doesn't have any bias, right? Which basically means that in an expectation level, on an average over a lot of data points, our model is supposed to give you exactly y is equal to x beta star and no extra error term, which basically means that there is no bias in the model. And variance is being defined as sigma square in, and again, why in? So we are defining it on based on an identity matrix, because every single parameter's variance is being defined by itself, independent of each other. First component's variance is sigma square, second component's variance is sigma square, so on and so forth, right? So this is how it is. So again, so bias is defined as expectation of beta hat minus beta star. So which is basically like like you're trying to get you already know beta star, and then expectation of beta hat will eventually give you beta star in the case of OLS, right? And you can see that like this is the closed form solution of beta star OLS, and when you see there's a beta hat OLS, and then you substitute y is equal to x beta star plus epsilon, and from here you get it as beta star plus x transpose x inverse x transpose epsilon, and you take the expectation of it, and this becomes the expectation of epsilon, which is 0, right? Expectation of epsilon is 0. So this just becomes beta star, like the expectation of beta hat OLS just becomes beta star, which basically means the bias is beta star minus beta star, so bias is 0. So for ordinary d square there is no bias, right? And when you calculate the variance, you calculate the variance in the same way, right? Which is expectation of beta hat minus expectation of so again this again is, so expectation of beta hat is a constant, which is basically the sample mean, right? So this is the sample mean, and this is one whatever beta you are sampling. So if there is a lot of variance in your data parameters, then this entire thing becomes very high. So again, variance means that how far you are from the mean. Like if there is a particular mean, then how far your beta is from the mean. That is what variance represents. So again, that is why we are taking square, right? So this transpose is basically the square of this matrix, and we are taking an expectation over it, and that is basically what variance is. So when we try to find the variance, we see that the variance is quite high, which is sigma square x transpose x inverse, which basically means that for ordinary least square, the variance is high and there is no bias. Now what happens in such situations is, if the variance is high, that means your model has a tendency of overfitting. Just remember this. This is a very important point to remember. It is intuitive and it is easy to remember as well. If your model has low bias and high variance, it has very high chances of overfitting. If it has very high bias and low variance, that means the model has underfit. Okay, so low bias, high variance means overfitting. Why exactly? Because again, low bias means your data points do not give any error. That means your training set has performed significantly well with the current regressor, which basically means that there is no bias, and then that basically means that again, with a high variance, which basically means that when we have like pinpointed our model to work only for the training data set, and it will not work for the test data set just because of the fact that the variance is very high, right? So again, so these things are like very fundamental machine learning concepts that sort of come to you. So here you see that the bias is 0 and the variance is like positive. But when you see ridge regression, here the bias, right, it is non-zero, right? So because you add a slack term and you calculate the bias, so you get the bias as something non-zero. But when you get the variance actually turns out to be lower than the initial variance because you add a lambda to it. So the variance, if you calculate it, it will turn out to be lower than the initial OLS variance. So the summary basically is that for OLS estimator, the bias is 0 and the variance is high. So this is unbiased, but it is a very high variance. But for regressors, you'll see that the bias gets higher, but the variance gets lower. And you'll find a point where the model stops overfitting on points which are very far away from the hyperplane, right? So it will not try to train on those points. That is the entire point of it, right? It will not try to make its parameters so high just to satisfy one point so that it fails on the others, right? So it has this entire thing like the regularization happening, which makes sure that the lambdas make sure that the betas are within a particular range. We use like shrinkage for those betas to make sure that like those are being shrinked towards 0. So there is no such parameter which becomes so high that that parameter is the only parameter affecting your result, right? So that is something that creates a lot of bias. Like one parameter affecting a result creates a lot of bias, right? And that is something that you do not. No, it does not. It makes sure that the bias is less. I'm sorry. It makes sure like your one parameter being very high, that makes sure that it feeds for that one particular misclassified training pool. It's like one of those training points is bad, and for that your model has to suffer. One of those training points in such a way that it does not represent your data, but just because of the fact that it is there in your training point, your OLS will still try to learn it. But your ridge and lasso will make sure that even if you learn that, it will not like overshoot towards it. It will not try to learn it a lot, so that ultimately it only learns well on training points which have been sampled from the distribution that we want. So at the end of the day, you will find a generalization risk which is also less and which will try to match the empirical risk. So this is essentially what regularization is, right? I tried to explain as much as possible.